Question 20 in Chapter 13 is very similar to question 19. It's also asking for three things, just like question 19 was. It says, for each of the following, give the monosaccharide. So that is the monosaccharide units. That's one thing. Monosaccharide units produced by hydrolysis. Hydrolysis is just when you break things apart, lysis, using water, hydro. So what two monosaccharides, here's one, here's another, what two are they that you would get if you break this bond here, break this apart? So that's the first thing. The second thing they're asking for is the type of glycosidic bond. The type of glycosidic bond, and that was, the glycosidic bond is the ether here that holds the two sugar rings together. So that's the second thing, and then the last thing is that they're asking for is the name of the disaccharide. Which disaccharide is this? Is this maltose, lactose, or sucrose? So here's a table of the three main disaccharides that you would want to know for Chapter 13. Maltose, lactose, and sucrose. They're all sugars. You can see the ending, OSE, that tells you that. And you want to know two things about each one. You want to know which monosaccharides link up to make it. In the case of maltose, it is glucose and glucose. In the case of lactose, it's glucose and galactose. In the case of sucrose, it's glucose and fructose. Notice that glucose appears in every single one. It's just the second monosaccharide that's different. So that's one thing you'd want to know. And the second thing you'd want to know is the type of glycosidic bond. In the case of maltose, it's an alpha-1,4 glycosidic bond. In the case of lactose, it's a beta-1,4 glycosidic bond. And in the case of sucrose, which we'll talk about more in this problem, it's an alpha-beta-1,2 glycosidic bond. Okay, so that's what you would need to know to solve this problem. I find that the first piece of information that you get, once you get it, everything else sort of falls into place, is the glycosidic bond. So let's hone in on that and see what we can tell about it. Now, one thing you'd want to do to help to identify what type of glycosidic bond it is number the rings. And how you do this is orient yourself by the oxygen in the ring. Go immediately to the right of that. That carbon is carbon number 1. Then go clockwise and number it 2, 3, 4, 5, and 6. That's one ring. Next ring. Orient yourself by the oxygen in the ring. Go immediately to the right of it. That's carbon number 1. Then number the ring clockwise from that. So 2, 3, 4, 5, and 6. So already after numbering the ring, we can see that the glycosidic bond, that highlighted green, is holding carbon number 1 on one ring to carbon number 4 on the other ring. And so this is going to be a 1,4 glycosidic bond. And again, glycosidic is a big fancy $10 word, but the glyco there is coming from the same Greek root as gluco in glucose. It's just, in Greek, it's just coming from the word for sweet. And so this is a bond that's holding two sweet things, in other words, two sugars together. So 1,4 glycosidic bond. The other thing you want to note about the type of the glycosidic bond is whether it's alpha or beta. Remember, the oxygen coming off of carbon number 1, so in the case of this ring on the left, that's going to be the oxygen in the glycosidic bond, could either be going up or could be going down, depending on what direction this oxygen attacked it when it went from being a straight chain to a ring. If it attacked from the bottom, then the OH goes up, and you have a beta isomer. If this oxygen attached from the top, then the O goes down, and you have an alpha isomer. The word isomer just means they're arranged differently in space. Two structures that are arranged differently in space. So in the case of this particular oxygen, the oxygen in this glycosidic bond, you can see that this oxygen is going down relative to this ring on the left. And because it's going down, this is going to be an alpha glycosidic bond. So altogether, This is an alpha 1,4 glycosidic bond. That answers one part of this three-part question. It answers what type of glycosidic bond we have. But from that, we can get everything else, because you would refer back to this table, which you would have memorized, and you would see that there's only one of these disaccharides that has an alpha 1,4 glycosidic bond, and it is maltose. So this disaccharide has to be maltose. And that answers a second question they had, the type of disaccharide. So this is maltose. This is floating around in beer all the time. Last but not least, they wanted to know the monosaccharide units. And if we know that this is maltose, then the monosaccharide units have to be glucose and glucose. So the two monosaccharides here, the one on the left and the one on the right, are each glucose. So glucose and glucose. Those are the monosaccharide units that you would get if you broke this apart. You cracked that glycosidic bond open. Okay, now they did include something else. They said, name the disaccharide including alpha or beta. When we gave this alpha, it was for the glycosidic bond, which was referring to this oxygen. We were looking at it relative to the ring on the left. But the ring on the right also has an oxygen on carbon number 1. Remember, carbon number 1 being right there on that ring. The oxygen here is going up. And so that ring is beta, because that OH is going up. Now it's the glycosidic bond that tells you what you have, so whether this oxygen here that we circled is going up or down, it's maltose. But if it's going up, then it's beta maltose, and if that were going down, it would be alpha maltose. Okay, let's try doing this one. Now this disaccharide should stand out. It looks different from all the others, and one thing that you'll notice is that it has a 5-membered ring. This ring on the bottom is a pentagon rather than a hexagon. As a shortcut, that in principles of chemistry, that means that this is probably sucrose. Of the 3 disaccharides you need to know, only one, sucrose, has a 5-membered ring. But there are other disaccharides in the world, and if you wanted to be sure this was sucrose, you would go through the same procedure as we've been working through for the other problems. So let's go through that just to show that that would work here and would be really valid. Now, the first thing we want to do is to identify the type of glycosidic bond. And to do that, we'll number the rings. Now, let's start with this ring on top. Orient yourself by the oxygen in the ring. Go immediately to the right of that. That carbon is carbon number 1. Then number the ring going clockwise around. So here this would be 2, 3, 4, and 5. Okay, that's the top ring. Now the bottom ring. Again, orient yourself by the oxygen in the ring. Then go to the carbon immediately to the right. We're going to consider that carbon number 1 for our purposes. And you could number it going clockwise to the right if you wanted to. We're not going to use those other numbers. Okay. Now, with these 5-membered rings, the carbon here immediately to the right that we were used to drawing as carbon number 1 actually isn't carbon number 1. Carbon number 1 is right here. You get these 5-membered rings because in a Fisher projection, now so far, so far we've had that aldehyde at the very top. And an oxygen around the bottom will come and attack it, and so you won't have any tail to the right here. But when you form a 5-membered ring, you don't have an aldehyde at the top, you have a ketone in the middle. And so when the oxygen toward the bottom comes around and attacks it, you're left with a little tail here. Now you would number these going from the top to the bottom, so whatever, 1, 2, 3, however many. And since this tail was really the top, this carbon here that was attacked is going to be carbon number 2. So if that long explanation was not immediately clear to you, in the case of a 5-membered ring, the carbon immediately to the right of the oxygen is carbon number 2. That's what you need to remember. And you'd go around the ring that way. Okay. So, now, if you look at the glycosidic bond, that's the bond holding the 2 rings together, that ether bond, oxygen single bonded to 2 carbons, you can see that it's connecting carbon 1 on one ring to carbon 2 on the other ring. So this is going to be a 1,2 glycosidic bond. It's holding 2 sugars together, so it's glycosidic. Now, we also have to look at whether the oxygen is going up or down. In the carbon on top, you can see that this oxygen is going down. And since it's going down, it would be alpha. So it's alpha for the ring on top. But in the ring on the bottom, since it's also the oxygen immediately to the right of this oxygen in the ring, that's always so important. In the ring on the bottom, it's going up. And so for the bottom ring, it would be beta. So this is both alpha and beta. It's alpha to the top ring and beta to the bottom ring. Altogether, the glycosidic bond is alpha-beta 1,2. So you describe this as an alpha-beta 1,2 glycosidic bond, and you'd put it all in front. So you'd have alpha-beta 1,2 glycosidic bond. And that would be our glycosidic bond. So that answers just one part of this question, but it is the most important part in the sense that now everything will fall together. Because when you refer back to the disaccharides that you would want to know, you would see that only one of them has an alpha-beta 1,2 glycosidic bond, and that is sucrose. So we know that this must be sucrose. So that is our disaccharide. Last but not least, because we know it's sucrose, it must be made of glucose and fructose. Those are the 2 monosaccharides that make up sucrose, so that's what we'd list here. This is going to be made of glucose and fructose. And unlike the other disaccharides, where the oxygen to the right of the OH to the right of the oxygen could either be going up or down, and so we either got an alpha or a beta out in front of the disaccharide name. For sucrose, this oxygen is already represented in the glycosidic bond, and so there's only one form of sucrose. You can't have an alpha sucrose or a beta sucrose, it's just this. This would be your answer, all 3 of these things.